Um, so office hours are usually typically Monday, Tuesday, Thursday. Um, they can all be attended virtually. So Mondays from 11 a.m. to 12 to noon. Tuesday, Thursday from 2:30 to 3:45. So I'll be having those for the next 2 weeks, next week and also finals week as well. And then the lecture times next week will be office hours as well. Yeah. If those times don't work for you, just let me know. And then we can make a time outside of that too. After next week, I'll be a lot more free. So I can meet like mornings or evenings, whenever works best for you.
Okay. I thought the plan for lecture next week was reviewing that.
You review MATLAB, open office hours, kind of same thing. Yeah. It's just project help, basically. Mhm. Yeah, so we'll start out with just open office hour, and then if I see some kind of same kind of trends, then I'll go over that as a class together. Yeah.
I think so, yeah. Yeah, I think it's doable. No. Yeah, a B.
What do you know like that? We can get. Plus it's like the bonus.
Oh, dude, I don't know.
It's like. More, so, it's, yeah, I think,
I'll try it, but yeah, I don't know.
I think it's
It's like, it's not that I can't, it's just the time constraint of this.
How many classes you taking?
4. And that work weekends, it's just like, I never really have enough.
Yeah, it's so. Yeah, I had enough time.
Oh, so you're not even like thinking about it or?
Well, I'm gonna try.
Okay.
Yeah. I'm okay with.
Yeah, that's, dude, I don't know, dude. He hasn't tested on this so far, so I'm probably just gonna skip it from that.
Should.
Yeah. Okay, okay. Yeah, I think I just haven't practiced good enough.
You have a solution.
Not yet, no.
Even though you don't have data to do this.
No, he does after, like, it's due today, but just kind of,
Oh, this is homework.
yeah, so,
Oh, I see.
yeah. I mean, I know all the spring stuff, but it's. Yeah.
All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Good, good. All right, yeah, we'll just get into it today. So announcement, I finished grading you guys' exams last night. I kind of just finished it right before I went to bed, so I didn't even get a chance to look at the average, but I think Canvas will show that to you. One thing you'll notice though is that, if you remember from the syllabus, I have 2 midterm grades for you. So whichever midterm you score higher in, I'll rate that for 30% of your grade, and whichever one you score lower in, I'll do 20%. I already did that for you. So if you scored better on the second exam, I've went ahead and swapped that into the 30% category. So your grade should reflect that. And so if you're looking online and you saw that your midterm 2 score was the same as your midterm 1, it's because I swapped the score. So everyone, if you could double check that, just make sure I'm pretty sure I swapped all those correctly, but just let me know, because quite a few you did better on the second midterm than the first one, which is great. Second midterm usually in this class is more difficult, so you guys are really good. Okay, so the plan for today, I'm gonna try to finish up our lecture notes on isoparametric elements. I primarily just have one kind of really big example to go through today. We're going to go through that example twice. And so I have the example with hand calculations just so that you can see how it's done. And then I have a code to kind of show you as well, that shows you implemented. It shows you it implemented in MATLAB. And in fact, you can use a lot of the same, not exactly the same thing, but you can use a lot of the same ideas from the code that I've posted in your final project as well. So definitely worth it to check that out. Okay. All right. So like I mentioned on Tuesday, we're very quickly approaching the end of the semester. So today's going to be a full lecture. I think we'll spend the whole time today doing the example. Whatever I don't finish today, we'll finish it up on Tuesday, which hopefully won't be that much. And then all of next week is just going to be working on the project. And so I think, originally what I had planned was to just do kind of open office hours next week during lectures. So for you guys to come in, work on your codes, ask me questions, things like that. But I think, some people have already kind of started asking me questions about the project. I think if I see some general trends in terms of people getting caught up in certain places, I think I'll probably address those together as a class. So definitely you guys want to I would definitely recommend getting started on the project, at least opening the code, see if you kind of understand what's going on. Just so that, we can be prepared for next week. Okay. All right. Any questions? Oh, I have the midterms, but I'll give those back to you at the end of class. Okay. Any questions I can answer before we get started? Okay. All right. So let's pick up right where we left off. And so we were talking about isoparametric elements. So like we talked about on Tuesday, the whole idea, so isoparametric elements is a very modern technique. Any kind of, modern finite element code uses isoparametrics to some degree, whether it be ANSYS or Fluent or Abacus is another popular one as well. Everyone uses isoparametric elements because it makes the construction very easy. And in fact, isoparametric elements was designed with kind of arbitrary geometry, practical geometries in mind. Okay? Because whenever you mesh, whenever you produce a mesh on an arbitrary geometry, the reality of the situation is that you're going to get a bunch of elements that are all very different from each other. Okay. Just as a very quick example, let's say we have just a very simple square domain, right? And so let's say that we want to discretize this, or we want to mesh this with triangular elements, right? So a mesh might look something like this. Right, I'm just kind of drawing things at random here. Right, your final project is very similar, right? So for the final project, we have a mesh that looks something like this. Right. Hopefully you kind of see that, each of these triangles that I'm drawing here are all slightly different from each other, right? They have similarities, and so they're all triangles, but they're different sizes, they're slightly different shapes, different orientations, right? And so each of these is going to produce a different element stiffness matrix. And that's just purely based on their different geometries. Okay. So whenever you're working with any kind of practical geometry, and you want to run a finite element simulation on it, this is just a reality, right? It's incredibly difficult, if not impossible, to get a mesh of all uniform elements where all elements look exactly the same. The only case where you may be able to do it is if your geometry is extremely simple like this. But if you have any kind of curvature or any kind of weird kind of shape to it, the reality is you're gonna have a lot of different elements. Okay. So the idea with isoparametric elements is to take like an arbitrary element in the physical space, right? Maybe an element that looks like this. Instead of trying to do the math and trying to do the computations on this element, which looks really weird, we're going to do kind of a step here where we're going to map this or transform it We're gonna map this onto an element where we know the exact size and the exact shape of the element itself. Okay? So, we're gonna, for our particular case, we're gonna map it onto a square, and we call this the parametric space. Because when we're in this space, because we know exactly what the element looks like, we know exactly what the shape functions look like, we can do their computations of this much, much more easily, right? So once we perform that transformation, we do most of the calculation, then we use kind of that same transformation to kind of pull it back, okay? Although that pulling back step is not that explicit. Okay? But that's the general idea, right? So we're doing kind of an extra step to our usual calculations, where we're performing this transformation, making it easier to perform our integrals, and then do our calculations now. Okay? So last time we introduced this idea, but we also derived expressions for the element stiffness matrix and the thermal generation term for our system. They're kind of big expressions, so I'm not going to write them again. But that was kind of literally the last 5-10 minutes of class last time. Okay? So today, what I wanted to do was I wanted to go over the general algorithm with you of how to do this, and we're going to do it with an example to kind of illustrate at every step to you. But also, before we do that, we need to go over how to cover the Neumann boundary conditions. Let's talk very briefly about that first. Okay. So let's talk about what our Neumann boundary conditions look like in the weak form. Okay. And remember, this is the 2D version. So our Neumann boundary condition in the 2D weak form, remember, was a line integral around the boundary. So it looked like this basically. So integral, line integral, like that. And it was W of X, Y multiplied by Q, E, S. Okay. And so if just to kind of refresh, remember, a line integral is basically like, if we have kind of a shape like this, a line integral basically means that we're kind of traveling along the surface, right? So we start at one place and we kind of travel along the surface just like this. So it's an integral that we perform in 2 dimensions, but or in 2D space, but we actually only travel in 1 dimension, if that kind of makes sense, right? Whereas like a traditional kind of double integral would integrate across the entire area of the space. A line integral just kind of goes around the boundary, just like that. Okay. All right. The important caveat to this is that we usually don't go around the entire boundary of the element. We only evaluate this whenever there is a Neumann boundary condition. Okay. So in most of the cases, we're not actually going to evaluate this because, for the most part, most elements, if the element is on the interior, so it's not even bordering the boundary anyway, we're not going to evaluate this. So we're going to ignore for all interior elements. And even for the elements that do border the boundary, you know, usually only one side of the element is borders the boundary itself. Okay. And it's not even guaranteed that if we even evaluate this, because if the element only borders a Dirichlet boundary condition or a constraint, then we just ignore this element, this integral entirely. Okay. So there's very specific cases where we actually evaluate this. And determining what those reasons are, or determining those conditions, is actually probably the hardest part of the code, probably the hardest part of the project. That's why I kind of saved it for part 2. Okay. So actually, let me put that here too. So this Neumann integral, this is for part 3 of the code. So kind of like the very last thing. Okay. So because this is a line integral, the way that we do the Gauss quadrature is going to be a little bit different as well. Because we're no longer doing a 2D Gauss quadrature. We're actually only doing a 1D Gauss quadrature from here. Okay. So just as kind of a very visual example, you know, let's say that we have an element that looks like this. And then let's say that the right side of this, the right side of the square here borders the Neumann boundary condition. Let's say we have a heat flux coming in like this. When we integrate this, or when we perform that integral, we're only going to do it on this edge right here. Okay. Because all the other edges on this element do not border the Neumann boundary, so we're going to ignore everything else. So actually, let me put that edge here, kind of blow it up again. And so our Gauss quadrature should only be applied on this line right here. So you can either do a one point rule, and so 1 point rule will put the one Gauss point right in the middle of the thing. And most of the time that's actually what we do. Or you can do a 2 point rule. So the 2 point rule maybe looks something like this. Okay. So you put the Gauss points kind of, you know, about 1/1/3 on one end, 1/1/3 on the other side. Okay. Or you can even do a 3 point rule. Okay. But the most common one that we probably do is just the 1 point rule. We just apply the Gauss quadrature right in the middle. Okay. So mathematically, it looks something like this. So the integral that we evaluate is line integral. So for the weighting function, we're going to plug in all of these shape functions. So we have n1, n2, n3, n4, okay. Xi and eta, xi and eta, xi and eta, xi and eta. Okay. We have our Neumann boundary condition value, which is the Q bar. This right here is our Jacobian, our 1D Jacobian, which you can see is just the length of the edge divided by 2. Okay. And then we're just going to evaluate everything right in the middle of this line. So we're going to evaluate everything at xi and eta at equals 0. Okay. Okay. I think this is better illustrated with an example, but that's kind of the general idea. All right, any questions on that? Okay, good. All right, so let's put it all together now. So now that we've kind of seen the element stiffness matrix and the element forcing vector under isoparametrics, let's see how to actually put all this into one algorithm. Okay, and this is essentially the algorithm that you're going to be implementing in your final project as well. Okay, so let's talk about the Gauss integration of the isoparametric rectangle. Okay. So remember, we're going to do the rectangle together in class, and we'll kind of do this in detail. The one on your project, of course, is not a rectangle. You're working with the triangular mesh for your project, but you would just apply the same logic, the same steps. It's just that, some certain steps will change because you're looking at a triangle. Shape function is going to change as an example. Okay. So for a rectangle, typically we apply a 4-point Gauss rule. And so it looks something like this. So here is our rectangle. Our origin is kind of right in the middle. So we have xi and eta. Okay. And then our 4 Gauss points are at the 4 kind of 1/√3 locations. So we have one right here, one right here, one right here, one right here. Okay. So this Gauss point right here, this is positive 1/√3, positive 1/√3. This one down here is a positive 1/√3, negative 1/√3. This one down here is a negative 1/√3, negative 1/√3. This one up here is a negative 1/√3, positive 1/√3. Okay. So those are our 4 Gauss points. Okay. And so we need to do a basically Gauss quadrature on those 4 points. Okay. All right, and so there's an algorithm for this. So there's kind of a step-by-step process to do this. But just to make it kind of visual and just so you can kind of see each step implemented, I'm going to explain each step kind of within the context of an example. Okay, so we'll do the calculations for one specific element, and it's just so that you kind of see how it all comes together. Okay, so this example right here, we're going to do the isoparametric algorithm. And we're going to do it on a rectangular element. Okay. So for this example here, let's draw the element first. So our element looks like this. We'll say this one's node 1, this one's node 2, node 3, node 4. Okay. Let's do the coordinates for each of the nodes. We'll say node 1 is at 0, 0. Okay. Node 2 right here, this is at 1, 0.2. Node 3 is at 0.8, 1. And then node 4 right here is 0.2, 0.9. Okay. So we have an arbitrary kind of quadrilateral here. So it's nothing, the sides aren't parallel or anything. Okay. So this is pretty typical of what you would see kind of in a finite element mesh. And just to make things clear, so what I've listed there are the coordinates for each of the elemental nodes itself. Okay. So this 0, 0 here, this would be basically like x1, y1. This is 1 comma 0.2. This is x2 comma y2. This 0.8 comma 1 is x3 comma y3. And that 0.2 comma 0.9, this is x4 comma y4. Okay. So those are the locations, so those are the coordinates of the node themselves. Okay. Because we're going to be computing the Gauss points. Remember, the Gauss points are different. So I want to kind of make it clear that these are a bit different here. Okay. In addition to this, we do have a Neumann boundary condition. It's going to be on the top face. So we're going to say we have a heat flux out on the top face here. This right here is our Neumann BC. Okay. And it has a value of Q out is equal to 5 watts per meter squared. All right. So to complete this, we also need our thermal generation function. So our thermal generation function S of x and y is 20x plus 10y. And we need our thermal conductivity K. So K here is going to be 10 watts per meters K. For that second K is Kelvin. All right. So this is our element, and what we're interested in. So let's say that let's find the element stiffness matrix and element forcing vector for this element. And the technique that we're going to use, of course, is the isoparametric technique with the 4-point Gauss rule. All right, so that's the setup. So this problem right here, this example kind of illustrates kind of the main problem or the main thing that you're going to be implementing for your project as well. Okay. So we're going to do it by hand first, just so that we can kind of illustrate every single step, and then we'll go over the code for it together, just so you can see how it's implemented in Math. Any questions on just the setup of the problem? Okay. All right. So let's go through the algorithm now. Okay. So the algorithm is a how many steps do I have here? It is a 10-step process. Okay. So the first step in the algorithm, which for this example problem is kind of already stated within the problem itself, but when you're writing the code, you have to do this yourself. Okay. So the first step is to establish and save all of the physical coordinates of the elemental nodes. Okay. So we've kind of already done that in the figure, but let's state it again here just to make sure. Okay. So this is we're defining here x1, y1, x2, y2. These are the physical coordinates of the node itself in the physical space. So x1 here is 0, y1 is 0. x2 was x2. x2 is equal to 1.0, and y2 is equal to 0.2. Okay. x3, what was x3? x3 was 0.8. y3 is 1.0. x4 is 0.2. 2, sorry. And then y4 is 0.9. Okay. All right. So that's really important because we're going to be using these coordinates several times. So you know, you want to make sure that you establish that first. Okay. Okay, so from steps 2 and onwards, at least for the next 7, 8 steps, we're going to be within a loop. Okay, because remember we're doing this for a 4-point Gauss loop. So that means we need to do calculations at 4 different Gauss points and then add them up together. So I'm going to do a loop here. So let's say repeat. Let's spell repeat. So we're going to say repeat the following. For each Gauss point. Okay, which essentially means we're going to write a for loop. Okay, we're going to write a for loop with four points. Okay, step 2. Step 2 is to establish the parametric coordinates of this Gauss point. So we have 4 Gauss points that we need to loop through, right? So our first set of Gauss points, xi1 and eta1, we'll say is we'll start in the bottom left. So we'll start with minus 1 over root 3, minus 1 over root 3. Our next set of Gauss points, xi2, eta2. This is a we'll go clockwise. So we'll go minus 1 over root 3, positive 1 over root 3, xi3, eta3. This is both positive 1 over root 3, 1 over root 3, and then xi4, eta4 is equal to positive 1 over root 3, negative 1. Okay, so those are all the 4 Gauss points we have to visit, but you know, we can only evaluate one at a time. Okay. So for each time that this loop iterates, or each time that this loop repeats, we're going to choose a different set of the Gauss points. Okay. So for now, you know, just for the sake of this example, I'm going to pick one, but just know that, you know, you're going to repeat steps 2 through 9 you know, for each of the Gauss points. So for now, let's pick this one. Okay. But just know that, you know, when we kind of repeat this, we'll choose another set on the next iteration. Okay. But just so that we can plug in numbers, let's choose that first Gauss point there, just for that. Okay. Okay. So that's step two. Step two is establish the Gauss point location. All right, step three. Step three is to compute the values of the parametric shape functions at this Gauss. So for our isoparametric element, we have our four shape functions. Let me go ahead and remind you of what they are at this point. Okay. So you have n1 of xi and eta is equal to 1/4, 1 minus xi, 1 minus eta. Okay. N2 xi and eta is equal to 1/4. 1/4 of 1 minus xi, 1 plus eta. Or excuse me, 1 plus xi, 1 minus eta. And 3 of xi and eta equal to 1/4, 1 plus xi, 1 plus eta. And 4 of xi and eta equal to 1/4, 1 minus xi, 1 plus eta. Okay. So those are our four parametric shape functions. The beauty of isoparametrics is that, you know, these are always going to be the same, right? These are always going to be the four shape functions that we're going to use. So for each of these four shape functions right here, we're going to plug in our Gauss point. Okay? So the Gauss point that we've selected for this iteration of the loop is xi is equal to -1/√3 and eta is equal to minus 1/√3. So it's just plugging those values. Okay. So we plug that in for n1, we get 1 minus 1/√3 times 1 minus 1/√3, all multiplied by 1/4. So we plug that in, we get approximately 0.622. Let me actually fill in for the first one just so you can kind of see it. So this first one here will be 1/4, 1 minus 1/√3 times 1 minus 1/√3. Okay. You plug that in, that's 0.622. Next, we do the same thing for n2. So n2, I'm not going to write out the full expression there. But if you plug in, you know, -1/√3 for xi and -1/√3 for eta, then what we get is 1/6. We do the same thing for n3. So n3, we plug in -1/√3 for xi, -1/√3 for eta, and what we get is 0.0447. And And then for the final one for N4, we actually get the same thing as N2, which is 1/6. Okay, so we're gonna use these shape function values in several points that. All right, any questions on what we've done so far? Okay. So that's step 3. So step 3 is, after you've established your Gauss points, compute the shape functions at that Gauss point. Step 4. Not only do we need the values of the shape functions themselves, we also need the values of the shape function derivatives. So step 4 here is to compute the values of the shape function derivatives at the Gauss point. We're still using our selected Gauss point of -1/√3 and -1/√3, but now we're computing the shape function derivatives themselves. Okay. So there's quite a lot here. So there's 8 values that we need to compute. Okay. So we need basically the partial derivative of each of the 4 shape functions, one with respect to xi and one with respect to eta. Okay, so let's do this first. So we'll do partial n1, partial xi. Okay. And so that expression there is a minus 1/4 times 1 minus eta. Okay. And then we have partial n1, partial eta. It's minus 1/4 times 1 minus xi. All right, we can go ahead and plug in. We can go ahead and plug in for this. And so in this case, they're both gonna get the same thing because our Gauss point has identical values of xi and eta. And so we get a minus 0.394 for the first one and a minus 0.394 for the second. And that's again, we get that by plugging in xi and eta into this. Okay, so we can do the same thing for a partial n2, partial xi and partial eta. Partial n2, partial xi is equal to a positive 1/4 times 1 minus 1 minus eta. Okay. And then partial n2, partial eta is a minus 1/4 times 1 plus xi. Okay. So once again, we can plug in the numbers for this. And so we plug in the numbers for this particular shape function. For this one up here, we get a positive 3.9, positive 0.394. And for the eta derivative, we get minus 0.106. All right, so let's do the same thing. Partial n3, partial xi, partial n3, partial eta. This one up here is going to be 1/4, 1 plus eta. And the one down here is 1/4, 1 plus xi. Okay. let's plug in the numbers for these as well. And so for both of these, we're going to get the same value of 0.106, 0.106, both positive. Okay. Then we have partial N4, partial xi, partial N4, partial eta. Okay. So these expressions here, we have a minus, is it minus 1/4, 1 plus eta. And then for the eta derivative, we have a positive 1/4, 1 minus xi. This top one here is going to be a minus 0.106. And the one on the bottom is going to be a positive 0.39. A little tedious, I know. This part's probably the most tedious. Just because we have to kind of compute a lot of things just by hand. But remember, in the code, in code, what you have to kind of be concerned about are kind of these expressions here. Remember the way we set up MATLAB, that you just kind of plug in the formulas into MATLAB itself, and then MATLAB will do the work of kind of plugging in the numbers for you. Okay? Right now it's a little tedious just because we're doing the plugging in ourselves. But I wanted to plug it in just to kind of illustrate to you kind of how to do these calculations. But when you do it with code, it becomes a lot more simple. All right, any questions on this so far? Okay. All right, so that's step 4. Okay. So all we've done so far inside the Gauss loop is we've picked a Gauss point, we computed the shape functions themselves at the Gauss point, and we computed the shape function derivatives. Now we're actually going to start to use this information for things. So step 5. Step 5 is to compute the physical coordinates of the Gauss point. Because right now all we have is just the parametric coordinates of the Gauss point itself, which is -1/√3, -1/√3. Okay? So this Gauss point also has a corresponding physical coordinate. Okay? And that kind of lives within the physical element itself. Remember, the whole point of this transformation is to do a one-to-one transformation, where every point in the physical domain is mapped to a single point in the parametric domain, and every point in the parametric domain is mapped to a single point in the physical domain. Okay? So if we go back to the original figure here, right? Actually, let me erase these for a second. Let me move them downwards. Don't worry, I didn't forget about the thermal generation. Okay. And so if we go back to the figure here, right? The Gauss point that we just placed is somewhere around here, about, right? It's somewhere kind of in the lower left coordinate of the element. We don't know exactly where. We know exactly where it is in the parametric space, but when we map it back to the physical space, we don't know exactly where it is. Okay. So we'll call the coordinates of this point xg, yg. Okay. Or x Gauss and y Gauss. So before we move forward, we need to actually compute the physical coordinates of that point itself. Okay. And the way that we're going to do this is we're going to use first of all, we're going to use the physical coordinates of the element itself, x1, x2, x3, x4, y1, y2, y3, y4, and we're going to use the shape functions themselves. We're going to compute using element coordinates, element nodal coordinates. Plus shape functions. It's actually an expression or the exact formula that we're going to use. We've seen it before. I think this is just the first time we've kind of seen it in action. Okay. So the way we're going to compute this, so we're going to have a formula for xg. Okay. We're going to have a similar one for yg as well. So the way we're going to compute xg is we're going to take x1 multiplied by n1 plus x2 multiplied by n2 plus x3 multiplied by n3 plus x4 multiplied by n4. Okay. Well, remember x1 through x4, these are the locations of the element node itself. Okay. So these right here. We obtained these in step 1 of our algorithm. Whereas everything, all the n's, n1, n2, n3, n4, okay, we obtained these in step 3. Okay. So we're just kind of combining both together to compute xg. Okay, so we plug in and let's see what that gives us. So xg is equal to x1 in this case is 0.0, n1 is 0.622 plus x2 is a 1.0, and then n2 is a 1/6 plus x3 has a value of 0.8 multiplied by n3 is 0.0447 plus x4 is 0.2, and then n4 is a positive 1/6. Okay. All right, so I just, it seems like, all those numbers there I got just from the steps that we did previously, right? So the physical coordinates, we outlined those in step 1, and then step 3 is when we computed the values of the shape functions themselves. So if we punch all that into, well, for now, we'll punch it into a calculator, but, code, we'll punch it into MATLAB, we get 0.2358. And then yg, we have a very similar expression, but instead of the x coordinates, we're going to replace it with the y's. Okay? So you have y1 n1 plus y2 n2 plus y3 n3 plus y4 n4. Okay. Once again, using the y coordinates of all of the physical nodes of the element together with the shape functions themselves. Okay. So we plug in the values for these, we get 0.0 multiplied by 0.622. Y2 is 0.2 multiplied by positive 1/6. Y3 is a 1.0 multiplied by n3 is 0.0447 plus y4 is 0.9, and then n4 is a positive 1/6. Okay. All right, so we plug all those in together, and what we get is 0.228. So now what we have here is the physical coordinates of the Gauss point itself. Okay? You may not, and so I'll be honest right now, for this, you won't need this in part 1 of the project, but you will need this in part 2. Okay. Basically, any function that requires you to evaluate x or y which for the most part is going to be your thermal generation function. You know, that's what you need this for. Okay. But for your element stiffness matrix, you actually don't. But, you know, I'm kind of showing you, I'm basically showing you kind of part one, part two, and I guess technically part three altogether. Okay, so that was step 5. All right, so next we have step 6. Step 6 is to compute the Jacobian. And since we're in 2D, our Jacobian is going to be a matrix. Okay. And I guess while we're at it too, we'll do one step at a time. Okay, so we went over the expression for the Jacobian last time. Basically, it involves the shape function derivatives as well as the nodal coordinates. Okay. Let me write out the expression here. So in this case, in this part here, we're going to do a matrix multiplication. In MATLAB, this is very easy to do. You just multiply the two matrices together. But you know, I'm obviously going to skip that part here just because it's a bit too much. Okay, so our Jacobian matrix is given by the following. So we have a 2x4 matrix of all the shape function derivatives. So you have partial n1, partial xi, partial n1, partial eta, partial n2, partial xi, partial n2, partial eta, partial n3, partial xi, partial n3, partial eta, partial n4, partial xi, partial n4, partial eta. Okay. And remember, all these shape function derivatives, we've computed these already. So these are not, you know, brand new things. So we did these in step 4. Okay. So we're basically using the values from step 4 and putting those into this matrix. Okay, and then what we're going to multiply this by is all of the nodal coordinates of all the nodes. So we're going to multiply by 4 by 2. So that's just to make sure that we end up with a 2 by 2 matrix in the end. Okay, and what we're going to multiply here is the matrix of the nodal coordinates of the physical nodal coordinates. Where we did this was step 1. Okay. So I'm not going to plug in the values here. It's a little bit too much to plug in, but I can give you the final result. So if you punch this into MATLAB and you do the matrix multiplication, you're going to end up with a 2 by 2 matrix. So plug in. We're going to plug in from previous steps. And what we get for the Jacobian matrix is the following. For this particular problem, we get 0.4576, 0.0894, 0.0576, and 0.4394. All right. So now that we have the Jacobian, one other thing that we're gonna need, or we're gonna need two things actually. Because this Jacobian is used for a couple things. Okay. So we have a step, we actually have a step 6A. I know it's getting a little confusing here, but we do a lot with the Jacobian. So, while we're here, we might as well compute everything that we need. Okay. So one of the things that we need is we need the determinant of the Jacobian. So you need to take the determinant of this matrix. Again, there is a function to do this in MATLAB, so there's, in most cases, there's no need to do it by hand. But we'll go ahead and do it by hand here. So remember, to compute the determinant of a 2x2 matrix, you're going to multiply the two terms on the main diagonal, and you're going to subtract the two terms from the off diagonal. Okay? The product of those things. And so if you do that for this case, we get 0.1959. So we're definitely going to use that later. So the other thing that we're going to need, actually for the very next step, is to compute the Jacobian inverse. Okay. So again, there is a MATLAB function for this. So as long as you have a numerical expression for a matrix, you can use MATLAB to compute its inverse very, very easily. It's just a function. Okay. Because if you remember from linear algebra, computing the inverse of a matrix is a gigantic pain in the ass. So we're not going to be doing that here. Okay. Okay. But if you run the inverse function within MATLAB for this matrix, so you're going to get 2.2428. I don't know why I included so many decimal places. Then minus 0.4563. Then minus 0.2940. And then positive 2.336. So three things that we obtained in this step. So we obtained the Jacobian matrix itself. We did that just by simple multiplication of two steps that we knew previously. We computed the determinant of the Jacobian, and we computed its inverse as well. All right, any questions on this so far? Okay. All right, so let's move on to step 7. All right, in step 7, we're going to compute the shape function derivatives, but we're going to compute the shape function derivatives in the physical space. And remember, what by physical space, physical space, whenever I mention physical space, I mean x comma y. And then parametric space or isoparametric space is I comma t. Okay? So we already have the shape function derivatives, but they're in parametric space. They're not in physical space, right? But in order to form the in order to form the element stiffness matrix, we need the shape function derivatives in the physical space. Okay? All right, so the matrix that we want is we want to form partial n1, partial x, partial n1, partial y, partial n2, partial x, partial n2, partial y, partial n3, partial x, partial n3, partial y, partial n4, partial x, partial n4, partial y. Okay, so that's what we want. All right? Because this is what we're gonna need to plug into the element stiffness matrix, right? We don't have that, but we do have the building blocks to to get this. Okay? So I believe we went over this expression last time, but let me go ahead and just remind you. Okay? So in order to get that expression there with the shape function derivatives in x and y, we're going to multiply two matrices that we have already, that we've already obtained in the previous steps. Okay. So the first matrix looks like this. So it's partial xi, partial x, partial eta, partial x, partial xi, partial y, partial eta, partial y. Okay. Okay. That first matrix right there may look foreign, but we actually have this already. Okay? Because this matrix right here, this is the Jacobian inverse. Okay? Which if you recall, just from step up here, this is step 6b. Okay. We have that already, so we don't have to worry about that. Okay. All right. Next thing we're going to multiply is this 2x4 matrix. And so we have partial n1, partial xi, partial n1, partial eta. It's always such a pain in the ass to write, but it's important. Partial n2, partial xi, partial n2, partial eta. Partial n3, partial xi, partial n3, partial eta. Partial n4, partial xi, partial n4, partial eta. Okay. I know it's a lot of derivatives, it's a lot of variables thrown around. I know. That's why I'm trying to keep things clear in terms of what steps we computed with. Okay. So if you look at these derivatives here, you'll notice that they're all shape function derivatives in the parametric space. Okay, which we've computed already. So these are shape function derivatives in parametric space. We did this in step 4. Yeah. Okay. Okay. So let's see, did I compute that for this problem? I did. Okay. So if you perform this matrix multiplication, and so remember we have all these values, we compute them in previous steps, we get the following matrix here. Okay. So for this matrix, for this problem, and you can plug these matrices in yourself and do the multiplication and verify, but we basically get the following values. You get negative 0.7039, and then to negative 0.8044, 0.932, negative 0.3634, 0.1894, 0.2164, minus 0.4175, and minus, or positive, excuse me, 0.951. Okay. So this is the result of step 7. And actually, this matrix, we're gonna use it quite a bit later. So I'm gonna give this matrix a name. So we'll call this BG. Okay. Where BG, this is just our matrix of our shape function derivatives in the physical space. Okay. That's step 7. Step 7 looks really intense, but in code, it's actually very simple. You have the matrices already, you just multiply them. Now we come to step 8. So step 8 is you typically only do this when you have thermal generation. So this is only for part 2 of the project and beyond. So if you're doing part 1 first, you're going to ignore this step right here, but I'm going to include it here just to be complete. Okay. And so in step 8 right here, what we're going to do is we're going to compute the value of the thermal generation at the Gauss. All right, so our thermal generation function for this problem here, S of x comma y. Let's see, it was 20x plus 10y. Okay. For the project, it's going to be a different function, but you can plug in any function here. So we want to evaluate this at the Gauss point. So S of xg, yg. Okay. So remember, we computed these values. Okay. I believe we did them in step. What step did we do that in? It was step 3. We did these in step 5. Excuse me. Okay. So if we plug in the values for that from step 5, remember xg, that value was 0.2358. And then YG was 0.228. Okay. So we plug in those values here, we get 6.996. Okay. All right, so with that, that's actually the last thing that we do inside the loop. And so if you remember, starting before step 2, we entered this loop where we're going to repeat this for every Gauss point. Okay. So steps 2 through 8, you're going to repeat for every Gauss point. Okay. And then once you're at the end here, we're going to say end the loop. Okay. So I'm not going to go through all the calculations again for the other 3 Gauss points, just because it's a lot, but you can kind of plug in and see. Okay. So once you kind of reach this point in the algorithm, okay, you basically repeated steps 2 through 8 4 times for each of the Gauss points. And so at this point right here, we are ready to construct our element stiffness matrix as well as the element forcing vector, but just the thermal generation. Part. All right, so just because we're almost out of time, I'm going to show you the expression just for the element stiffness matrix first, and then we'll go over the element forcing vector on Tuesday. Just because we still need to do the Neumann boundary condition as well. Okay, so for the element stiffness matrix, our element stiffness matrix looks like the following. Okay. Okay, so our element stiffness matrix is K sub E. Okay. Our K sub E is going to be summation. Remember, that's the whole point of Gauss quadrature, is that you evaluate everything at the Gauss points and just sum them all up. Okay. Okay. In this case, we're going to do a summation of 4 terms. We have I is equal to 1 to 4. Okay. We're going to take BG transpose. Remember, BG here, this was the result of step 7. But we're gonna have 4 values from step 7, so 1 for each Gauss point. Okay. We're gonna multiply this by K. K is our thermal conductivity. We're gonna multiply this by another BG. So once again from step 7. Okay. We're gonna multiply this by the determinant of the Jacobian. Okay. Remember, this was step 6A. And that's for this particular Gauss point, so that's G. Actually, instead of the summation being over I, let's do it over G. Just to be consistent with the terminology. Sorry about that. Yeah, so I made just one small change right here. I changed that I to a G. All right, and then the last thing that we need for Gauss quadrature is we need to multiply by the weight, Okay, so this right here is the Gauss weight for that point. Which, if you're using a 4-point rule, the Gauss weight is just 1. But if you're going to use a 1-point rule or a 9-point rule, then that's going to be different. Okay. All right. So that's the algorithm, right? And so we kind of went over kind of almost every step. So when we come back on Tuesday, we'll finish up this algorithm. There's just a couple more steps that we need for the element forcing vector. I'll show you what the code looks like just so that you can see how it's implemented, and then we'll get started on the project. Okay? So I think what I'll do is that on Tuesday we'll finish this up, and then just I'll give you kind of an introduction to the code itself, just so you know kind of how everything kind of works. All right, so thank you guys for coming today. I hope you guys have a good rest of your weekend. For those of you in person today, I do have your exams, so you can come pick it up. But if not, I will see you guys next week. Yep.
For the global surface measurement for the project. Where some should we use this like the brand?
Exactly. Yeah. That's exactly what you should do. I think the only thing that's complicated is that the connectivity you have to use the one that they give you instead of one that you produce yourself. But the format.
Oh, yeah, you're right.
The format of the connectivity is exactly the same. So that's why we kind of went through that whole spiel for the.
We did that one with the. So like. Each node has like, not all of them, but like most of them, like 6 elements.
Yeah.
So we do. You're saying like the approach we get with the Franklin?
Exactly. Yeah. So that approach that we did is actually flexible for situations.
Oh, it is?
Yeah. Because remember we just added on to whatever we used that updated notation. Yeah, so when we did the frame, it seemed like a very roundabout way of doing it back then, but
Yeah.
that's precisely because I had this in mind, so that same algorithm is.
That makes sense. Thank you.
I'm trying to figure out how to get the XY positions for each.
Yeah, so for that one, you're gonna use, there's another data structure that the code produces called nodes. So that data structure has all the X, Y coordinates.
I'm not really familiar with that.
Okay, so if you look, actually, let me see if I can pull up the code right now. Actually. So no potatoes.
So that's the only stuff we.
No, I missed.
Actually, let me just.
This one.
Yeah, that one we all got.
This one.
Okay, yeah, that
Okay.
one.
So in this code right here, you can see here that we have this data structure called nodes and a data structure called connectivity. So you need these two together to get x1, y1, x2, y2, and so on and so forth. So actually, let me kind of comment this out.
Oh,
Let me
okay.
run this code just so that just to show you.
Yeah, wherever it says.
Yeah, that's fine.
So apparently I messed up there.
I didn't have this equation. I was freaking. So dumb. So I was trying to do it by hand when I was. I derived it wrong. Yeah, I did.
Let me just copy.
Oh,
Oops.
yeah. I think it's.
Oh, dude, I made such kind of. Dude, that was. Dude, that's so, nah, that's such a stupid mistake. So let's read to the power of this, I'm like, okay, just multiply that by 4 and take that all of it to the power.
Oh, no.
Okay,
I think it's.
so when you run the code. there's-
Yeah, but I mean,
there's
yeah,
data
right, it's a
called
silly
nodes.
mistake.
So this has all of the XY coordinates. So for this mesh right now, there's 740 nodes. Actually, let me actually visualize the mesh for you, just so you can see as well. So for this one, let's print all of these. Okay. Okay, so you can see here that, for every element has 3 nodes associated with it, right? So let's say, look at this element right here. It's connected to nodes 731, 145, and 732, right? So if you want to get the XY coordinates of these, so let's say that we want to get the XY coordinates of node 145. We'd go to the nodes matrix right here. We go to column 145. And we can see that the X coordinate for node 145 is 0.2121, and the Y coordinate is 0.4892. So you'd basically access it this way. Now, the question is, how do you know? Like, say that, because the way that we're writing our code, we're doing a kind of element by element, right? So we're kind of visiting one element each time. So how do you know, which nodes are connected to which element? That's kind of what this part of the code up here does, right here. So the first thing is for this particular element, because remember we're looping over every single one.
Right.
We need to find out which node numbers are connected to this one. So for this one, you're going to use the connectivity matrix. So I'll give you, so someone came in office hour than that. I'll give you kind of the same or the same kind of code that I gave you. So let's say that you want to get the index or the node number for the first node in that element. You use the connectivity matrix, so connectivity, and you do 1, comma IEL, right? Because IEL here, just like for our frame code, this is the IE, excuse me. This is the index for the node that we're visiting, and we're going to look in the first row of that matrix, right? Because if you look at the connectivity matrix is actually formatted in the exact same way as we did in our frame code. So for this particular mesh right now, we have 1,340 elements. And so if you look at the structure of this, there's 1,340 rows or columns, excuse me, in this here. And for every column, there's 3 entries. And so each entry in this matrix here is the node number of that particular element. So for instance, element 1 is connected to nodes 683, 570, and 572. So you would first get the node ID number right here, or the node index, and then you would use that with the nodes vector down here. So let's say you want to get x1, right? So x1 would be nodes at 1 first row, and we want to get the node index IND1, just like that.
Okay.
Yeah, and so you kind of repeat that for each one. So for this one, you'd have 3. So you have IND2, IND3, just like that. And then you'd have x1, y1, x2, y2. I can type y2. What? y2, x3, y3. So you have kind of similar expressions for all of this.
Thanks.
Yep.
Oh, okay. That's a good question. Inside the second for loop on the, so on part 1, there's a message that I had asked you about it, Tuesday. So we noticed that when we were doing our code, if you move the for loop, the elements, like the elements of the matrix changed, whether you had a loop or not. And it was because we were doing basically KLM is equal to KLM plus.
Yeah, I mentioned this section of.
Oh, yeah.
So because of that, we're getting different answers. We're basically like.
Talk about, I think, a factor of 3.
Oh, okay.
So
Are you multiplying by the Gauss weight too? Because I think for triangles, I think the Gauss weight is actually 1/3. Let me see. Yeah, the triangle is weird because the area of that triangle is actually 1. It's not 4.
Yeah.
Find them out.
Yeah. So for the project, we're using the 3-point Gauss rule.
Mhm.
So the weights are all 1/3. So you have to multiply each contribution by 1/3.
okay.
Yeah, it's weird because for the square, the actual area of that isoparametric square is 4.
Yeah.
That's why our Gauss our Gauss points are 1. But for the triangle, the area of this triangle right here is actually 1/2. And so that's why you multiply everything.
Okay. Interesting. Okay.
Yeah, Gauss quadrature is weird, just like
Yeah.
stuff like that. But try multiply by 1/3. I think you'll get your answer.
Okay. Thank you.
Mhm.
You
Yep.